Hey folks, how's everybody doing today? Oh, happy Wednesday. Alrighty. Man, we'll see how well it goes tonight. I wasn't able to make it last night. Every time we go somewhere, I pick up a cold. It's awful. Since this whole like not being around people for a year and a half and then going out and being around people, it's been weird. So I'm propped up on some cold meds right now, but should be fine enough for tonight. We'll take a look. All right. So we got a couple things tonight. We're going to talk about trees that we didn't get from last time, but we've covered heaps already, essentially. And then we'll look at specifically binary search trees and balancing search trees. And then we should be able to get to graphs as well. I don't think that'll take too long here. We're not going to get super deep into graphs. There's a lot of graph theory you can get into, which is super interesting. We're just going to touch on some of the basics of graphs. And then next week is set aside for you to work on your final project. And then the week after that, we have our presentations on Zoom. So I don't have any lectures planned for next week unless we need some of that time to finish up the topics tonight, which we'll see how long my voice pulls out. But I think we should be able to get through most of it. So then next week you'll have time for your final project. I'll be happy to meet with you folks during the regular class time if you want, or we can make arrangements to meet other times as well. Just let me know it's going to work for you. And then the goal is in 2 weeks from tonight, you'll have your final projects ready to present via Zoom. Yeah, Dusty, it's weird. Apparently, it's useful to have your voice when you're teaching. I mean, I could type all I want, but I don't know. Would speech to text or text to speech? I think I've got some text to speech settings, right? Can I do that? Look at that, I've got a voice pack. Well, that's for it doing the things. That doesn't do my reading. I don't know. I can't quite type as fast as I talk, but I can get relatively close. If you folks ever bored, there's a fun game called Type Racer that you can play, and you can all hop in and like race each other at the same time. It's kind of fun. So you can just match up with other people online. Yeah, I gotta sign in here. I think it's Aerochinsky. Did I get it? Oh yeah. Okay, there we go. So my average speed 90, not fantastic, but 90. Not too bad here as a typer. If you folks ever want to play sometime, we can definitely play on Type Racer. All right. Anyway, that's the wrong one. Not Discord. You don't need that one. Okay. Here we go. This one here. Yeah, that was great, Dusty. I mean, the idea was good. I didn't think it would do all the keys. I thought it was just for special keys, but I did not read the instructions well enough. I have since had to change my password. So that was awesome. Those are good times. Those are good times. And you know what? Hey, we all make mistakes, right, Dusty? I think I got it changed quick enough. It did backfire. Yeah, that was dumb of me. But I don't know. I use a lot of keyboard shortcuts. So I like being able to show, like, hey, this is, I'm hitting Control Alt F for format or something like that. So I don't know. I'm a big fan of typing less and using more shortcuts. So shortcuts are fantastic. All right. So the idea here with trees, so far, all of our data that we've done so far, either whether or not it's been in the bag or a list or even with a hash table, has been relatively one-dimensional. I'm glad, Rishi. Yeah, there's a lot of content. We go through a lot of chapters. There's a lot of material when it comes to data structures and doing some of that algorithm analysis. And the whole idea why we study it, excuse me, so that we understand better the performance trade-offs. just looking at the table and saying, oh, here's the performance of all of these data structures. They're like, oh, okay. I mean, anybody can look at the table and see that, but spending some time actually like digging into them and actually building some of them out, I think helps solidify the how the stuff works, which is kind of fun. All right, so let me close this one out. And we'll start a new project, and we're going to talk about trees tonight. In 2353. Excuse me. All right. And the idea with the tree is that we now have a different structure to our data. So again, with the bags, everything goes in. With the list, the order matters. With the hash table, we're just having a collection of items, or a set is our right? We don't allow duplicates. You have a set. But with a tree, you can actually now start representing relationships in data, which is really cool. Man, is the NetBeans the one that's laggy? Every time there's not, it's a little laggy here. What is going on? Yeah, oh, it's NetBeans background scanning projects. Why is that so slow? It's me. I think it's just lagging here because of NetBeans. Yeah, it's eating up all my CPU. Thanks, NetBeans. Settle down now. All right, thanks, Code. All right. Oh, and they did ask me to do another pitch for fall enrollment. Hopefully you folks are close to done, and there's not many other classes you'll need. But fall enrollment is still up and running. We got a lovely email from our dean, who's a really nice guy. I do like him. He said, hey, we've got these 4 different online classes with wait lists 15 people deep. Should we open up more online sections? And does anyone want to teach them? And that's teaching online sections is a whole other story versus the in-person stuff. And we've got contract nonsense, and everything is a big deal, apparently. But so we don't know. It seems like the preference is you folks like online classes because they filled up fast and not the in-person sections. And we don't know if that's just a general preference or if that's because you don't want to go back to in-person because of this pandemic, like we don't want to go back to in-person, or I don't know. But if you have any insight, I'd be happy to hear your thoughts as a little sounding board for your thoughts around in-person versus online classes and the flexibility and whatnot. So, all right, awesome. You got everything you need for fall, Rishi? Okay. So with a tree structure here, we no longer have a list. Yeah, I mean, the big push we heard from everybody was everyone wants to be back in person, and then all of our online sections filled up fast. So we got confused, but I don't know if anyone actually knows what's going on. Yeah, missing out on the lab stuff is hard. My friend and colleague over at Auburn Hills uses Zoom and puts people in breakout rooms and says, go spend 20 minutes together in a breakout room working on something, and then we'll come back and talk about it. And to me, that just sounds awful in an online format. And like trying to manage that in this online format and trying to not have people drop off in that 20 minutes, and I don't know. But maybe I haven't tried hard enough, and we could do better with online lab style things, but I think that's a problem that is yet to be solved. So yeah, the flexibility is nice for sure. And hopefully moving forward, I think I mentioned I'm going to try and make my courses this high flex style, where I'll be in person if you want to come in person. I'll be on live on Twitch if you want to be synchronous online, and then I'll just export all the stuff out to YouTube like I've been doing for anyone who wants to be asynchronous. And then you just take your pick. If you want to come in person 1 week, great. If you want to be remote 1 week, if you want to be asynchronous 1 week, go for it. Whatever works for your schedule, because scheduling stuff is hard. It's really hard. All right, so a tree structure. Right. Now, typically when we look at trees, right, we kind of imagine this tree here, and they've got like branches with all these leaves and other branches coming off of it, right? Like you kind of imagine trees here, right, with all their limbs and whatnot, and branches and branches and branches, and as high as it wants to go, right? All these branches out here, like that. So usually this is like the base of the tree here, right? And then it's got all of its roots down below, and all the grass around it here. But when we draw tree structures, we do them upside down. And I don't know why, but that's just kind of what we do. So we say the root of the tree is at the top. This is the root. And a tree stores data in a hierarchical fashion. You know, I haven't talked to Dr. Othman in quite a while. The last time we met was in the winter semester, like early on in the winter semester. We only have like 2 department meetings a year, or discipline meetings a year. The whole thing is, I'm still new to it. Later this month will actually be the 1-year mark of me being a full-time prof here at OCC. So, all right, so the root node is the start of the tree. So root is the start, right? It's essentially the start. Oh, great! I'm glad it's going well. Yeah, we got really lucky getting him. He's a real smart guy, real sharp. Seems real nice too, real personable. I never had him for a class, but it was funny. Apparently, I actually took over for Bill Shannenberger when he retired, because things like take a year to actually fill a position. And I had classes with Bill back when I was at OCC years and years and years ago. It's actually not even that many years ago, but it's been a couple. So the root or the start of the tree is here, and then a root then has children. So each or node in a tree, so maybe you might call it a node of the tree, has some number of children. So you kind of see this hierarchical structure. And what's cool about a tree is that it's recursively defined. So each one of these children here is also a tree with some n number of children. And n could be 0. It might have no children. It might have 1 child. It might have 50. Right? So this is just some number of children at each level or each generation of the tree here. So the main tree, the top of the tree, is the root with no parent. That's the start of the tree. And then we talk about trees. They have heights, and each node is at a given level. So this node is at level 0, this node is at level 1, if these ones have children over here, right, these trees are at level 2, right, so you have levels. Levels are essentially how deep you are. And the height of the tree equals the max level. So whatever the max level is the height of the tree. That's not level. So whatever the maximum level is, that's the height of your tree. Now trees are really cool, again, because we can store this sort of hierarchical data. Just like when we talk about inheritance, right? You have, here's the parent, and you can have child classes, and those child classes can have other child classes, and whatever, and everything eventually works its way back up. Remember, like in Java land, it's object. Everything is an object. So object might be the root of this inheritance tree, right? And you can use trees to represent all sorts of data, right? We use these sort of tree structures, hierarchical structures, all the time in the real world. So it's really cool to have a way to represent that sort of data. So anything at your same level is a sibling. Essentially, I guess like this one is not really a direct sibling of this, but they're all at the same level. So we can store data with that, and you'll have a parent and child relationship here. So instead of like our linked lists that had left a before and after, or a previous and next, we now have a parent relationship to the parent node, and the parent has a child relationship to all the children here. We can store these lots of different ways. It's really common to use linked nodes. So we might have a linked node tree where you have a node, and node has a bunch of children, and node has a parent. So node would have a single parent of a type of linked node tree is the parent, and it's going to have a list of children which are all of type linked node tree as well. Right? All of its children nodes we should be the parent of, and when you get to the node with no parent, you know that's the root of the tree. And you can also talk about these a subtree. This portion here, right, because we're recursively defined, this is a subtree, a portion of the main tree. So a subtree rooted at this position here is a subtree. This here all by itself is a subtree. It has no children, but it's still a subtree because every node in the tree is another tree itself. Right? It's a tree made up of trees, which kind of makes this idea of like drawing a picture of a tree a little silly because it's not really trees of trees. You have branches, but again, we use this tree metaphor because that's sort of what this looks like. Again, we do it upside down, but that's sort of what it looks like here when we do our links. So we could, if we wanted, we're not going to spend a lot of time doing this here, but we can do a linked tree. And then linked tree is going to be made up of a bunch of nodes here. So we're going to have a private class for node of type T, right? It can store some type of T data, right? And then node will have a private linked tree of T parent and probably a private array list of type T, or I'm sorry, a linked tree of type T. Yep, this is an array list of linked tree of type T children. Because you can have n number of children, right? So you'll have some list of children here that we can have. And then we'll have our public gets and sets. Insert constructor, children, sure. And then we'll insert, nope, not a logger. That was not what we wanted. We did not want logger. We wanted insert getters and setters. Insert setters. And then we also want another constructor, because if you don't know what your children are, that's okay too. We'll do a no argument constructor, and then we'll do another constructor that takes just a parent. And we can just have a bunch, right? So this can call to this with null and a new array list of type tree of T. And then this one should call this with parent and new array list. So if you don't give me a parent, I'll assume it's null, and I'll instantiate that new child list. If you give me a parent, I'll take that. Take your parent, I'll make a new array list. Or if you already know what your children are, great, we'll take them. And then we maybe want a way to like add a child. We could do that sort of thing. We got lots of options here. So then linked tree, then we'll have a private linked tree of type T as the root. Right, and then this one needs constructors and all sorts of good stuff here. So it'll make a T object, and the root will equal a new linked tree of type T, excuse me, given the object. All right. No, sorry, a new node. I'm sorry, we need a new node. That's right, this is a node. New node. Oh, that's right, we also need the T data. My goodness. For T data. Have a T data. Data, no parent. T data with the parent, and then a T data. One of these. We'll always have the data. Data equals the data. All right, so you give me the data, then, oh man, come on, format. Data, comma, parent. I got really ugly there, I'm sorry. Yeah, so you need the data here so we can have gets and sets for data. Insert code, getter for data, and a setter for data. All right, so then the root is a new node of T given the object. Just the T data. Nope, sorry, this is a node. new node of T. So linked tree is the main version here, and then we store these nodes with all the links there behind the scenes. Right, and then we can add children and we can do all sorts of fun stuff here. But this lets us now have this structure, and then we can add a public tree of T get root. No, this just needs to be T root. That's our root dot get data. Bring back the root data, or we could give them the tree itself, and we could walk these nodes. And so we got lots of options for how we want to traverse this sort of tree structure. But again, this is a generic or an N tree with N number of children. And now it turns out these ones are actually a little tricky when you have N number of children to manage and deal with, but they can work. Right? We can just add objects and figure out that sort of thing. Here we have the root. Yep. So if we go and add a child, then right, we would add it to the nodes list of children. Right, we'd add more linked trees of them, and they'd have their own nodes. So we store all this data in this sort of hierarchical structure, but these ones are a little trickier. So it turns out it's a little easier here if we use what's called a binary tree. Binary linked tree. And a binary linked tree is different than an N tree in that you only have left and right children. So you're limited to have two options. So binary are two options. You can have a left child and you can have a right child. And that's it. And each one can have a left and each one can have a right. Now you don't have to have a left, you don't have to have a right. But again, this you're limited to, so it's no longer an N number here. It's not an unknown. So we'll know exactly how many possible children you might have. Excuse me. So we talked about binary trees a little bit when we jumped into heaps, because I got out of order there and got really excited to talk about heaps when we talk about priority queues, because they work so well. But with the binary tree, again, we're only going to have a left and a right child here. So our binary linked tree then, can of type T here, we'll store T nodes. So we'll have a T data. Now, in this case, we don't necessarily need that linking node itself, because we have, we know binary linked tree of type T. The parent, like we can just keep the data right in here. Linked tree. I guess we could have done that with the other ones too. Left child and a private binary linked tree for the right child. I guess we could have skipped all the node stuff too for the other one, could we have? So you'll have the data, and then you'll know your parent, your left child, and your right child. And then we'll have ways of getting these values back out. So again, we can add some code here. Construct. We definitely need one with data. And then we need one with data and a parent. And then we can do one with all the options here. Again, I prefer to do more pass the data and you give it null. Call the next constructor. This with data parent null and null. Just call the constructor, kind of chain them together here. Make that life a little easier. So you always have the data. If you have a parent, great. If you have left and right children, great. If not, we'll just assume they're null till we know otherwise. Then we can add all of our gets and sets. Not the logger. I don't know why I keep clicking logger. I'm sorry. Not the one I want to click. Add all of our gets. We can add all of our sets. Now we might not actually want all the sets here. Actually, maybe we'll leave all the sets blank. So only get data here. And then maybe we add a method here, like add child, add left or add right. So public. How will we do a Boolean add left T data? or a public boolean add right given t data. So if our left child is equal to null, we're going to return false. Because we can't do that, right? If we already have a left, we can't do that. It'll say, hey, if I have a right child, I can't do that. Otherwise, then, now we can make a new left and right child. So then we can say my left child equals a new binary linked tree given the data, and this is the parent. Remember this constructor that can take the data and a parent? So we are the parent of our left child. And we do the same idea with our right child. We'll say our right child is a new binary linked tree with the data and us the parent, and then we'll return true. Yes, that worked. Return true. Yeah, that worked. No, true. I don't know how I got the clone. Excuse me. And then we will have a get left and get right. So, oh no, we have gets, right? We have a get left child and get right child. Yeah, get left child, get right child. Good. And get parent. Okay. So then to calculate the height of a tree here, right, we can figure out the height. So public int height here is, remember, height is how many generations do we have until we got the no parent. So we have int height is 0, and then we're going to loop, right? So we're going to say we'll have a binary linked tree of t is the current, is this, really, and then like while current dot get parent does not equal null. Let's keep on going. We want my height. So if I have a parent, height plus plus, and then current will equal current dot get parent. If get parent is null, then we're done. We return our height. I'm sorry, Harishi. I keep getting bit by those defaults here. Yeah, I'll make sure I get that added. Let me make myself a note here. Is for switching and hashing. And I guess trees. Cool. What was that? Trees and ESTs and graphs. All right, as far as we'll get. Right, so for our height, right, we just take those links and keep walking to see how far we get. Right, that's the height of our tree. Or that's the current height of the tree, whatever we're rooted at. No, that's actually, no, that's our current level. That isn't the right. So the height is the maximum level of a given node. I guess that's not really what we want to do here. So we want to go the other way. Right? We need to go see through all the children and count how many generations we have. So this one was no good, sorry. We can't go from the parent. That would tell us what our level is. Let's make this a private int level here. So that's the level that our given node is at, a given tree is at, right? So how many times can you go up? How many parents are in that chain? So public int for height then, well, we need to go through all of the children, right, and find the max level of all of the children. Right, that'll calculate the height of the tree, the maximum level. Well, to do that, we need to go and we need to find every child and go through and figure out the height, right? Excuse me. So we need to find the max. I think there's a math up. Math max, yep. Math max of the right child dot level, and left, or I guess left should be first, right? Left child dot level, right child dot level, find the max of those and add 1 to that. right? So the height of my children. So if I have a left child, great. If I have a right child, great. So I guess we should check. I guess we should make sure those are not null first, right? So if we have a null left child or a null right child, those are gonna fail. But the level of our children. So if we have, oh, I guess we don't even need to add the 1 to, do we? Let's see. No, we want to do height. Okay, so okay, I'm sorry. I'm getting ahead of myself. So we want to check if we have a left child. Left child does not equal null. Then we're going to have a height of the left child. We have an int for max child height. I'm going to start it off at 0. And then if it's not null, it'll equal this one dot height. And then if right is not null, my right child is not null, not equal null, then the max child height will equal the max of max child height and right child dot height. Then we can return the max child height. Okay, is that going to be right? So it starts off at 0. I think we're going to return that +1. I think I ought to do it here. So if we're going to check the height of each one of these here. So if we have tree, let's see. So if we have a tree with no children, right? Left is not null, false. Right is not null, false. We're going to return 0 + 1. Nope, that's not right. So it's still going to be 0. If we have one child, then I think here we want to do the +1s. +1. So if we have one child, or a left and a right, either one, right? Left and right. We're going to ask for the height of this one. And it's going to say start off at 0. Okay, left is not null, true. So then I'll get the height of the left child. Now, left child has no children, so we're going to return 0. So we'll get 0 + 1. That should be good. And then right, 0 + 1. Okay, that should be good. Now, if we add another child here, when we go to the left height, we're going to get 0 + 1. Max height is 1. Then right child says, okay, what's the height of the right child? Height of the right child is going to go here and say, okay, what's the height? Well, no left child, and then right child is there. So then it's going to go here, recursively call. This one has no children. Yep, this ought to work here. I think that ought to work. So we don't need to use this level check here then. You know, I think we could keep it. But we use this recursive call here because we don't know how deep this is going to get. We just need to follow each of those paths, left and right paths, to find out which one is the max. Now this is actually doing a little bit of extra work, but that's okay. There's a cool way you can optimize this where you know if your node has children, then you cannot be the max. So what you want to do, you want to go through your binary search tree or your binary tree, and you want to find all the nodes with no children. Right? So this one is a node with no children, and this one is a node with no children, and then you'll find the max level of those. So if you can have a way to iterate through and go through all of the children or all of the nodes in the tree here, you can find the ones that have no children and just find the max level there instead of having to look at every single one. It saves a little bit of time there. Excuse me. We should be able to find the height of our tree that way. All right, so let's see if we can use our tree here. So we can add some data. So let's look at trees. Let's make a new binary linked tree of, how about type integer? We can store some ints. To make a red-green tree during Christmas? That's a good joke. Sorry, my sugar is high. Oh, goodness. Maybe I just need to wait. I'll wait a little bit. Still trying to figure out how to be a bionic man. We'll call this our numbers. The new binary tree, type integers. And we make a new binary tree, we need to give it the data. So which one is first? So how about we do 10? And we'll take our numbers, and we're going to add left. Add left. What do you want to add to the left? How about 20? And we'll take numbers, and we'll add right. About 30. And then let's take the binary search tree of type integer. We'll call the left child equals numbers.getLeftChild. We'll take the left child, and then we'll add left. How about we add a 40? And then maybe we take a binary linked tree of type integer for the right child. That'll be numbers.getRightChild. And then right child, we can add, how about we add 50? You can put a heap of presents underneath. I like it. I'll add right. So if this works for us here then, right, we're going to have one more child over here. This one should have a left. We did 10, we did 20, we did 30, we did 40, and we did 50. 50. Right, so the height of this one here then, right, this is 0, this is 1, should be 2. So we can print out the numbers.height. So the height of the tree, rooted at 10, this number's one here. Goodness. Plugin's got all messed up here. It's compile on save thing. It does not work for me. Oh. Left child is null. Uh-oh. Add left. Oh, did I do the wrong thing? Binary linked tree? So we're all good there. Where's my add left? Add left. New binary tree, and then data in this. Left child, right child. Oh my goodness, what did we do wrong here? Numbers get left child. Trees at line 12. Left child dot add left. Left child is null. Numbers dot add left. Left child is a new. Oh my goodness. If it does not equal null, I had these backwards here. I'm sorry. So if there is something already on the left, we can't do it. Otherwise, we can add. All right. That was my problem. There. We get a height of, uh-oh, height is 3. I think we did one too many adds here. We have a child. We have a child. We have a left. That one has a left. I don't know, let's put it in debug mode. We'll add a breakpoint. We'll run in the debug mode. See what we get. All right, here we go. So we're at the binary search tree. Our data is 10. We don't have a parent. We have a left. We have a right. The left child is 20. The right child here is 30. Looking good so far. So left is not null, it's true. So then our max child height, then we want to step in. Now we're recursing here. So now the this that we're at is we're at 20. 20 has a left. So it's going to recurse again. Now we're at the tree rooted at 40. It has no left, it has no right. So it's going to return 0. So when we return 0, we're going to get 0 plus 1 is now the max child height. Now we're going to check the right. Does this have a right child? It does not, right? Remember, this is the tree at 20. Here, this one here does not have a 20. So its max height is 1. So that now we have 1 plus 1. So now our max child height, where'd it go here, is 2. Now we're going to check, do we have a right child? This plus 1 is in the wrong spot. It should be right child height plus 1. So the right child height plus 1 or the left child height. That was the problem. We added 1 to the wrong spot. Okay, now 2. So then if we want to go add another child here, so we can say, hey, I want the right child equals the right child get right. And then the right child, right, oops, that's a type of binary linked tree. And then the right child dot add, how about we add left? How about we add a 60? So now the height should be 3, right? So if we take this right child and we add a 60 to its left, we add 60 over here, right? That's in the 3rd level, so our height should be 3. Cool. And again, you just keep on recursively figuring out that height from there. So we can add left, we can add right, we can work all our way through here. Okay. So this is interesting, right? And again, binary trees are nice. They're a little easier to work with because they have lefts, they have rights. There's other operations we can do, like you can add an entire tree to one spot, that sort of thing, but we don't need to bother too much with that. All right, so general trees, right? A binary search tree then is a binary tree with this particular format. And what's cool about a binary search tree, our binary search tree, is it is in a particular form that follows a rule. With a binary search tree, everything on the left is less than your node. Is less than. Oh my goodness, I can't draw. Less than. Everything on the right is greater than. Actually, this way. And here's the node, or the data. So you have some data, and everything on the left will be less than, everything on the right will be greater than. So if we're to try and add all those numbers again here, we don't follow that pattern, because 20 is greater than 10. It can't be there. 40 is greater than 20. It can't be there. But we could say, okay, if I wanted to add a 10, and then we go, oh, hey, let's add a 20. Is it greater than or less than? It's greater than. Okay, go to the right. We add 20. Then we add a 30. Greater than or less than? Oh, it goes to the right. We add a 30. We add a 40. All right, goes to the right. 40. We add a 50. Goes to the right. We add a 60. Goes to the right. This, technically here, is a binary search tree. This 10, 20, 30, 40, 50, 60, you know, all down the right here. It is not in a very good form, though, because it's essentially just a big chain, one big link. Like a better form here might be if we had, say, 40 here, and then maybe it had 20 as a child there with 30 and 10, and then maybe it had 60 over here and 50 right here. So this here is a better formed binary search tree. The idea that, I mean, and by better formed, I mean it has the minimum number of levels. So minimizing the number of levels you have is going to give you good performance. And we'll talk about that in a little bit. But the idea that everything on the left, right, is greater than, and everything on the left is less than. And that is a recursive definition all the way down. So I can never put, so this child over here can't be 15 because it is not greater than 20. right? That's not allowed, so we can't have that there. Right, so the idea is what we do when we go add these things, we just recursively call add to the next level, and the next level, and the next level. So binary search tree of type T, where T implements comparable of T or some T. Goodness, I just got to go copy that because I can never remember. We want it's like comparable of super T or something like that. Yeah, that's fine. That's all fine. Comparable, right? Yeah, there we go. T extends comparable of T. Goodness. T extends comparable, where some type is comparable to super type of T here. So as long as they're comparable, we can put them in a binary search tree. And I need a way to tell greater than, less than, or equal to. We'll have the T data. We'll have a binary search tree of T, the left child. We'll have the binary search tree as the right child. And these should all be marked as private. Right? And we'll also have the parent as well. Of the parent. We can steal our constructor out of our binary linked trees, right? All these constructors are still perfectly valid for us. These just need to be binary search tree types here. Binary search tree. Okay. We're stealing all those. Now with the binary search tree, when we go to add some data, right, we just have like void, or probably a Boolean, right? Add T data. So if the data matches, we're going to return false, because again, this has to be a set here. You can't have duplicates. So if the data equals this data, and probably dot equals, right? Equals this data, return false. Otherwise, if data dot compare to my this data is less than 0, it means it's less than, right? A negative number means less than. I guess we could do all, we might as well just do all compare to's, right? Why not? Because we're talking about compare to. If it equals 0, no good. If it's less than, then we're going to try and add it to the left. So if our left child is equal to null, then left child equals a new binary search tree of type T, given the data, and this is the parent. If left tree is not null, right, our else case here, or actually we can just return true here and then we'll be done. Otherwise we're going to return left child dot add the data. To say, okay, you're less than, but I have a left child. So left child, you go figure it out. Right? If we're not equal to and we're not less than, we have to be greater than, right? My else case here. We're going to check if the right child is null, then my right child will be a new binary search tree of type T, given the data, and this is my parent. We can return true. If we didn't do that, then otherwise I'm going to return my right child dot add the data. And this is all dependent on this being a recursive structure where every child is another tree. So if I have this form and I say, hey, go add 15, right? 40 is going to say, okay, you're less than, do I have a left child? Yes, I do. Okay, so left child, you go add 15. 15 says you're less than, okay, do I have a left child? Yep, left child, you go add 15. 10 now says, okay, you're not equal to, you're not less than, you must be greater than, do I have a right child? No, okay, now I have a right child. 15 is my new right child. Excuse me. So now we have a new node here, and we've added it. So it follows this recursive definition, so we can add any number we want to this binary search tree form. right? And because we follow this recursive definition here, you either add it to the left or make the left child add it. If we don't have a right, add it to the right. Right child. There we go. Helps if you can spell things right. So if we're equivalent, false. We can't do that. Otherwise, if we're less than, check the left. Otherwise, check the right. That's we add data. So there's no adding to the left. There's no adding to the right. It's just this is what we do here. And then we can steal this height option here. We can steal level. Sure. So again, the book does a good job here with, this is a binary search tree, of using inheritance, where we keep like a superclass that has a lot of this stuff defined, and then we just inherit from it. I find that to be a little confusing. I know it's more work here. Oh, we don't even have a get parent. Do we? We should add a get parent. I will just say parent. Here, we're in the class, so we have full access to these private values here. We don't need to use the gets. Okay, let's see, what do we have? Yeah, I fixed those. Okay, we fixed those. So now what we do, though, now when we have a binary search tree, right, we could say whether or not we contain something. Right, we could say, hey, do we contain this value here? So public Boolean contains t data. Similar idea here. We're going to do, are we equal to, less than, or greater than? If we compare to equal, we're going to return true. If it's less than, and left is null, then we'll return false. Oops, sorry. So if it's less than us, and we're null, we're going to return false. I don't have it because you can't be less than if I don't have a left child. Right? Otherwise, we're going to return whether or not my left child contains the data. And then on the right child, if we don't have it, we're going to return false. We don't have the data. Or does my right child tree contain that data? So either I'm going to find it where it's true, or I'm going to get to a point where I don't have a left or right child, and I'm less than or greater than. So we say, hey, let's try and find, say, the value 16. We're going to say, are you 16? No. Are you less than? Yep, go to the left. Do we have a left? Yes, we have a left. Okay, now here, are you 16? No. Do you have a left? Yes, we do. Okay, so go over here. Are you 16? No. Are you less than? No. Are you greater than? Yep, we're greater than. Do you have a right child? Yep, go here. Now we're here. Are you 16? No. Are you less than? No. Are you greater than? Do we have a right child? There's no right child here, so we return a big fat false. We didn't have that. Let's say we wanted to search for 50. We say, okay, are you 50? No. Are you less than? No. Are you greater than? Okay, do you have a right child? Yes, we have a great right child. 60. Are you 50? No. Are you less than? Yes. Do you have a left child? Yes. Okay, ask the left child. Are you 50? Yes, we're going to return true. We found it. Now what's really cool here is that because the way that the data is stored here, right, each level, right, level 0, level 1, level 2, level 3, stores the level number, or 2, to the level number of nodes. Right, there's 2 to the 0, 1 node. There's 2 nodes at the next level. There's 4 nodes at this level here. There's 8 nodes at the level after that, on and on and on. So, right, 2 to the level number of nodes is how many pieces of information we're storing at the level. And when you do one of those contained searches, it's a binary search. Right? We're cutting off half, well, not exactly half, but right, we're cutting off the other side of the tree in our search. So if it's less than 40, we cut off all of the right tree of 40. If it's less than 20, we cut off all of the right tree from there. On and on, just like when we had a sorted list and we started in the middle and we cut off half, we're doing that same sort of thing here with a binary search tree. So finding something in a binary search tree is generally really fast, assuming it's what we'll call balanced. And balanced means that we don't have this sort of chain structure. Where's that chain? We're like, oh, there it is. Where we're not like 10, 20, 30, 40, 50, 60, where we are so heavily weighted on the right side. And there's a couple cool ways of looking at how you can balance a search tree, in that you don't want one side to have more nodes than the other side. And you're not exactly going to be always even, but there's some different strategies you can look at to make sure one is not overly weighted compared to the other one, not too many more nodes. There's some common ones. There's a red-black tree you can look at, or an AVL tree that you can look at that do some really cool things behind the scenes. We're not going to bother actually writing our own for that to do the balancing. But if you can get balanced, right, what's really cool is that your search for something is then logarithmic in n, because you're cutting off half each time. Your insert is also logarithmic in n. And this is a sorted data structure. So this is sorted data, right? Because we're maintaining the sorted order here. When you insert into sorted order, right, you just need to find where it fits, left, right, left, right, left, right. And we're working our way down a logarithmic in n number of operations. Because the number of nodes in a tree based on its level grows exponentially, right? We get a nice little exponential growth here. That's a terrible exponential curve. Don't tell my algebra teacher. Right, but with one level here, with 2 levels here, we get this many. With 3 levels here, with 4 levels here, with 5 levels, 6 levels. We're essentially doubling every time we go. Right, that's a really fast curve. Here, so this is levels, and this is nodes. Right, if you're going to look at the graph like that, the number of nodes and the number of levels you can have. So search and insert is really quick, and remove is really fast too. Remove is log of n, because all we need to do is we need to find the node, right? Find where it is, and then remove it. And there's some interesting swapping that happens, that takes place to which piece is going to replace it here. So the trick to replacing a node, right? We can't always just say, oh, just take the thing on your left and put it in the right spot, because like if we, this is kind of ugly now here, I'm sorry, let me redraw it here. So if we had 40, and then we had 20, and we had 10, we had 15, we had 30, and we had 60, and we had 50. So removing a node with no children is super easy. I could remove 50, no problem. No work has to happen at all. Not a big deal there, right? If 50 had one child, if we had like 55, that's really easy too. I'm just going to put 55 in its place. 55 in its place, and this one's gone, right? So 0 or 1 children is really easy. Removing 20 here, though, is hard, because I already have 2 children, so I can't just say, hey, this child over here, take its place, because this one already has a right child. So the trick to that, what you do is you're actually going to swap values with the largest child on the left. So you look to your left, and you say, who is the furthest right? So you go left once, and then you go right, until you run out of children, and then you swap. So we're going to take 20 out, and we're going to put 15 in its place, because the furthest right child will have no more right children. So at most, it will have 1 child, and a 1-child swap is really easy, and a no-child swap is even easier. You just take it out. So to remove an item, right, we're going to replace it with the furthest right node on the left, because that's the greatest node on the left. So you just go left 1, and then you go as far right as possible when you replace it. And that'll help keep you in this nice binary search tree form. So our inserts and our removes and our searches are all logarithmic in n. So we get really good performance for a sorted data structure. Remember when we had a list that was sorted, inserts were really slow because it had to bump n number of items across with an array-based list, or finding the location was really slow. If it was a linked-based list, we didn't have to do any bumping, but we had to go find it. We couldn't take advantage of the binary search that said, hey, look in the middle, cut half off. Look in the middle of that, cut half off. Look in the middle of that, cut half off. With a linked-based list that was sorted, you had to go through n operations to find where it belonged. With the array-based list, you had to go through add operations to bump everything down when you added that or when you removed something. So the array-based and the linked-based sorted lists were really slow, where a binary search tree, again, sort of assuming we get that sorted, balanced structure, right? This is a big fat star here, right? Star balanced. If it's balanced, we'll get logarithmic performance, which is really nice for a sorted structure. Remember, with our hash tables, our dictionaries, we didn't have any sorts. Right? We just threw stuff in and we kept it. It was really fast at that, right? It was constant time for that when we hash. But there was no order, and it was definitely not sorted. So if you want something that's sorted, a binary search tree is really fantastic at that. Right? And then we looked at when we did our heaps there, instead of actually using links where we have the left child, we have a right child, you can store all of this data in an array, right? And your indexes then of your children, right, were like 2 times your position for the left child and 2 times your position or your index. Index plus 1 for the right child, that was left and that was right. And your parent was like half your index, right? So at index 0, 1, and 2. Was it half minus 1 or something like that? Or half? I'd have to look again what we did. Right? 2 times plus 1 or something like that. 2 times plus 2. I forget. We could look and see what it was. But you do some quick arithmetic and you find what it is. So you can also store a binary search tree in an array-based form if it's balanced. And that way you're going to get better memory performance, space performance, because you don't need to keep all these links to left child, right child, and parent throughout. Because remember, then that's 3 extra memory references. 3x the memory reference. And in a 64-bit system, that adds up really quick for every node. So again, looking at space performance, not just time performance or complexity, here is really nice. All right, I got a little after 7. We've had a lot of fun talking about trees. Why don't we take a break? We'll see, what else do we have here then? I think we're pretty good talking about trees. We can look at talking about graphs. We'll see if we want to do any, I'll skim through those real quick, see if we want to cover any more on the trees real quick. If not, we can move on to graphs. Okay? All right, we put some music on, and we'll be back in a little bit. Take about 10 minutes. That puts us at 11:19 or so. Hey gang, welcome on back. Alrighty. So I did have one last thing I remembered I wanted to show about trees here. I want to look at how we can traverse a tree. There's a couple different ways of going about traversing a tree. Let me zoom out here. Again, usually we look at them in this tree form, and this makes a little bit more sense. So there's an in-order traversal, there's a pre-order traversal, there's a post-order traversal, and then there's a breadth or level depth totally forgetting the term here. It's a breadth traversal. So we would go all of level 0, all of level 1, all of level 2, all of level 3. And again, depending on what we're using the tree for, the different ways of traversing them make certain sense. So the book goes into a really big example doing a pre-order traversal and using like an expression tree. And I always find that one really confusing. But the most useful one is an in-order traversal. So for in-order traversal, it's a recursive call. So we're going to go left, and then when we have no more lefts, we'll do the center. We'll go left. After we do the center, we do the right. So from 40, we're going to go left. So we're at 40, so we call in order at 40, and it goes left. Then we call in order at 15, it goes left. We call in order at 10. There is no left, so then it'll print itself, or it'll iterate over itself. So it'll give us a 10, and then it'll go right. There is no right, so that one's done. So we did 15. We went left. Now we're going to do itself. We get the 15. Let me stack them up here. We get the 15, and then it goes right. So then we're at 30. It has no left, so it prints itself, or iterates over itself. It has no right, so we're done there. We're done there. We did the 15. Now we're at 40. Then we get 40, and then it'll go to the right. So it goes to 60. 60 then wants to go left. Left gets to 55. 55 has no left, so we get 55 back out. And then it has no right. It's done. We get 60. 60 is done. 60 has no right. So you can see in a sorted tree, the in-order traversal gives us the sorted order. When we iterate over them. Again, we skipped over a lot of the iterator piece. You can go back and take a look at that if you want one of the interludes here. We're just going to do a, I don't know, how about a string in-order traversal. So we're going to create a string. So I'll have a string builder for the result. String builder. So we're going to go left first. Then we're going to do center, right, ourself, and then we're going to go right. You know what? Actually, this is okay. Let's forget that. Let's just do void here. We'll do in-order traversal. We'll just print ourselves out. I'd set a quiz for last week. I think we'll have one for this week as well. This will be the last week of quizzes. So I'll do the searching and hashing, and then trees, BSTs, and graphs. That's what I thought I had said. That way we'll cover all the chapters in quizzes. So our in-order traversal, then we're going to go left first. So we're going to call in-order traversal, or if our left child does not equal null, we'll call left child dot in-order traversal. In-order traversal. Then we'll print ourselves. Print out our data. And then if our right child is not null, is not equal null, not equal null, and then we'll call our right child dot in order traversal. In order. So this is actually the easiest one here. Yeah, I'll post one. And sorry for not getting it in. When I make a quiz in D2L, it defaults to hiding it, which I guess is a nice default because like if you're still working on it, you don't want it to publish right away. But then I don't notice that it's hidden because I'm dumb. This whole not being in the classroom and like having that regular routine is still throwing me off. I still have not gotten used to this remote learning thing. My apologies. I'll get that added. There's no big rush on them. So you can take extra time on them if you need them. All right, so then I can make my tree, and let's see, we made our tree, didn't we? Tree is this one here. I'll print, oh no, we just call, right, numbers. Oh, we didn't even do a binary search tree. Binary search tree, BST equals the new binary search tree. And we're going to add a bunch of numbers, right? So we added 40, and then BST add, we added what, a 20, and then BST add, we added a 10, right? And a 15, and a 30, and a 60, and a 50, and a 55. I think it's all the things we added. And then we can call in order traversal. And it should print it out in nice formatted order here. 3 was the height, right? So 10, 15, 20, 30, 40, 50, 55, 60. We get the nice in order search. So the other orders, a pre-order traversal, does itself and then the left and the right, and a post-order traversal does your left and your right and then itself. Just a funny way of doing it. If you want the breadth first, like level by level, you would use a queue where you add all the children to the queue and you print them out, and you add all of those ones to the queue and you print them out. There's some fun ones to look at, but again, it kind of depends on how you're storing the data. Right, and I think that's good for our trees. Again, there's a little bit more to it, especially the balanced search trees, doing some of those rotations and things to keep you in a sorted order is fun, but we're not going to go build our own. The AVL tree is about as complex as we want to get, or the red-black trees. Trying to recreate those is a little bit obnoxious, and we don't really have the time for that. Right, so then we're going to move on to looking at graph data, and this is our last data structure. And a graph lets us store, it's like connections between nodes. So what's cool about graphs is you'll have nodes and then you'll connect them. Or these will be vertices with edges. So you have a vertice and you have an edge. So a vertice is like a node on the graph, and an edge connects them. Right? So a lot of times we'd compare this to like airline routes. You might say, okay, so from this city, this is the vertice, you can go to this other city. Right, so Metro Detroit is a big hub for Delta, so Delta flights can get you from Metro Detroit to lots of other locations. If you want to fly to somewhere that Delta doesn't fly direct, right, if you wanted to get to this city over here, maybe you take a Delta flight to here, and then Delta would fly you from there to there. Right, this sort of idea, you can follow the paths here, you can follow those edges to take one vertice to the next, to the next, to the next. That's essentially the graph, right? That's a graph data structure. And you can do lots of really cool things with it, right? You can have them all be connected, right? Or maybe you even have a graph where like a node or vertice is not connected at all. That's a disconnected graph. If you can do an entire loop of a graph, right? You then have, oh my goodness, there's so many terms for these. You gotta remember all these terms. And by remember, I mean look it up. You'd have a connected graph here, right? So connected means you can get from any one vertice to any other vertice. You don't even need the full loop here to be connected. So with connected, it's any vertice to any vertice. You can travel, right? Travel from any one to any. So it doesn't mean it's easy, but you can get to it. A complete one means every vertice connects to every other vertice. So complete graphs are not as common, right? So complete is every vertice to every vertice, instead of any vertice to any vertice. So it's not that there's any possible path, it says there's every possible path here. Right? And then a disconnected graph is when you can't connect between them. So vertices are adjacent if there's a path between them. And sometimes graphs are just, here's a connection between both of them. And other times, graphs are directed. You say there's a path this way and this way only. So you can get from C to D, but you can't get from D to C. Right? So a directed graph essentially you have one ways. Right? If it's a directed graph, you're going to have one-way routes. Otherwise, it's just a connection. Right, so maps are a lot of times, right? We would say you could follow the roads or like the vertices between cities. Airline routes are common ones. You could imagine kind of a maze as vertices and graphs, or vertices and edges, where like as you're traveling through a maze, every junction, right, is a vertice, and you might connect to different junctions to different locations in that maze. Course prerequisites is another fun one, right? You can't take CIS 2151 until you've had CIS 1500. Right, so it's a directed graph here. Right, 2151, you can get from this one to this one, right, on and on, so you can follow that path. And then to take other courses here, you should have this course, and maybe you need another course from over here. Not very many of ours have more than one prereq, but maybe you might. That sort of thing. So graphs can get really tricky. You can store lots of really interesting data in graphs, and then you can traverse graphs. So two big traversals here for graphs are breadth first or depth first. So breadth first starts at a vertice and then goes to every next vertice. And from there, tries the next every possible vertice. And then from there, so almost like a tree structure, right? We're trying all of these, but remember, you might have vertices then that connect backwards. So you have to keep track of, hey, have you already been to this vertice or not? Because you don't want to get stuck in a loop. If you get stuck in a loop, bad stuff happens, right? So you have to spend additional time tracking which vertice you've been to, or if that node has been visited a lot of times. So you have to be careful with that. Yeah, so the other thing, like, as we're looking at these, you can also have a weighted graph. So if we were to draw that, from, right, here's DTW, here's MCO, over here is LAX, right, or something. This is my terrible version of the country, right? You might have a certain weight here between these, and your weight probably is the number of miles, but again, it doesn't have to be, right? It can be whatever your graph data is representing. You might have a weight here. So the distance from DTW to Orlando, let's see, DTW to CO miles. See if we can figure that. There we go, 961. I knew I could do that, 961. And then maybe the distance from DTW to LAX, 2283. There we go. Wow. 2283. This country is a lot bigger than I realized. 2283. And MCO to LAX. LAX miles. 2535. 2535. Right, so there's different weights here, different distances. Right, so to get from LAX to MCO, to go through DTW would be the sum of that, right? 2283 plus 961. Right, it's going to be more than the direct. Obviously, it'll be more than the direct route. But as you are plugging in all these different possibilities here, we can go to all these different airports. If there's not a direct flight, like say we wanted to add another one out here, I don't know, was it SLC, like Salt Lake City, right? And maybe we have another one, I don't know, Chicago is O'Hare, right? I forget what their code is, OH, something or other. Right? Depending on where you want to go, you might take a different path, because that's either the least number of miles, or for an airline point of view, they might care about passengers, right? If all of their planes to MCO are full, Well, they're not going to send you to MCO to get to an airport over here, maybe in Louisiana, if that one's already full. But if their plane to O'Hare is less full, and then O'Hare has room here, they're probably going to send you here. So you can do different things for weights. You do lots of interesting things. And there's a really classic problem in computer science called the traveling salesman. Traveling salesman. And the idea with the traveling salesman is he wants to hit all of these different cities across the country here. Right? He wants to go to, I don't know, whatever it is, every capital in the country, or sure, whatever it is. Right? And all of these you can get pretty much anywhere from anywhere. Right? And the idea is, well, how do we find which is the shortest possible route for this traveling salesman to get to every possible city that he wants to? Right? And there's all sorts of fun computational things here. You can get more into this, so you can get crazy in depth in this problem. And actually, just recently, I think it was maybe even last year, someone finally came up with a way to improve this algorithm, and it was huge news for computational computer science. That no one had really thought that it could be done. And it turns out they didn't improve it by much, but just the fact that they could improve it by just a little bit was huge, because they thought they had already done the best that they could for this traveling salesman problem. But you would have to do a traversal, and you'd have to check every single path, and then check every path from that path, and every path from that path, every path from that path, and add them all up. No, that actually wasn't a dad joke, Dusty. Sorry, that was real. Where was it? I think it was an ICPC. PC traveling salesman algorithm improvement. Was this it? Facebook Watch Live. No, that's probably not what I wanted. Is this one it? No, that was 2012. That wasn't it. No, this was recent. This was really recent. It might not have been from ICPC. Nope, that was wrong. That was wrong. Got the wrong word. Yeah, there's a bunch of different algorithms. You can study all sorts of different algorithms for it. Someone just did it, though. Man, okay, I don't know. I don't know. It got passed around, but I don't have the Google foo to find that at the moment. But you just have to search, right, and find which is the best possible path to get there. And there's all sorts of cool things. In an algorithms analysis class, you'll do even further study on this sort of stuff. This is typically a 300 or 400 level class. You can go even farther. You can write your own and then see which one's good, which one's bad, that sort of thing. So it's all sorts of fun. Really interesting stuff to it, and being able to optimize those sorts of pathfinding is really cool. And pathfinding is huge itself, just for all sorts of cool things that we do, especially in artificial intelligence and like game AI sort of things. Pathfinding is huge. And of course, we'd like to break computer pathfinding and kind of take advantage of that in games, but that's okay. So if each of these had a weight, right, to calculate it. So your breadth first traversal says start with one node and connect every other possible path from there. Depth first says we'll go from one and then go all the way to the end first. So just follow as far as we can get on this traversal. So like if there were nodes over this way, and if this one's connected, it's just going to go as far as it gets first. It's going to go the depth first, and then it's going to try other possible paths, rather than the breadth first tries like every level as we go. There's different ways of traversing those graphs to see what's going to work for you there. So finding your shortest path for weighted or unweighted graphs, lots of good stuff there. and then actually implementing a graph is really neat. What we typically do is we will have just a list of nodes, or a list of vertices, and then it will have an edge matrix, which is really just a two-dimensional list, right? So it says what it says here. So then at row 0, row 1, 2, 3, 4, 5, and on and on and on. Right, and then at 0, 1, 2, 3, 4, and 5. So if we were to have a graph here, right, of vertices 0 and 1, 2, 3, 4, and 5. So if we had these kind of connections, like that. So you'd say 0 connects to 1. And if it's weighted, right, you put the weight in here. Otherwise, you just say, hey, it's connected. So 0 connects to 1, 0 connects to 2, 0 connects to 3. Okay? 1 connects to 0, 1 connects to 2, and 1 connects to 4. Right, for 2, 2 connects to 0, 2 connects to 1, 2 connects to 4. Okay, for 3, 3 connects to 0, 3 connects to 4, 3 connects to 5. 4 connects to 1, to 2, to 3, and to 5. 5 connects to 3 and 4. So you'd store that information, right, in your matrix or your two-dimensional list. You're like, all right, how do they connect? Right, and if these were a directed graph, maybe then we might say 0 connects to 1, but 1 might not connect to 0. Right, if we have a directed graph, right? So you can also store the directed information this way as well. Maybe 1 connects to 2, but 2 doesn't connect to 1. That sort of thing. So to do our traversals then, right, we could start with 0, right, and we would traverse from to 1, 2, and 3, right? Add that to our breadth first. And for each one of those, all right, where does 1 go to? 1 can go to 2, and 1 can go to 4. All right, where can 2 go? 2 can go to 0, 2 can go to 4, and on and on and on. So we just kind of take each row as we go with that adjacency matrix, right, or the edge matrix. So which nodes are adjacent to which nodes? You know, that list of adjacencies. So each piece here, right, each entry here is essentially a vertice. I'm sorry, not a vertice, it's an edge, right? An edge. So every time there's a mark, you have an edge, right? So we can draw it, or we can just have the list of our nodes, right? And then we can have that edge matrix. Oh my goodness, I'm throwing my stuff here. This little pen is really fun. So does that part make sense for graphs? Again, we don't need to get super deep. You'll get more into it if you're continuing on in computer science, in like a 300 or 400 level class, to do more graph theory, all sorts of fun stuff there. We don't need to spend too much time on it. We want to understand what it is, not necessarily reinventing the wheel here, because as we get more complex, right, trees get more complex, graphs get more complex, actually writing our own gets to be a little prohibitive versus, you know, the linked lists weren't so bad. We could write our own for those, or for array lists, we could write our own for those. We could do our own queues, we could do our own stacks. All right, so I think we reached about the end of our content then. That was 29 chapters plus appendices and interludes. My goodness, folks. And we did all of that in 13 minus 1, 12 weeks. You folks are amazing plowing through the material like that. Let's take a peek at our course objectives and see if we've hit all of our speed run. Yeah, I mean, summer semesters are rough, especially without having like a week off. So for critical thinking, right, we can use information to develop conclusions and solutions. We apply knowledge to the assigned task. We accomplish the assigned task. We understand the implications of relationship between ideas. Can you take a problem and solve it? This is the art of computer science, right? How do I take all the tools in my toolkit and solve problems with them? Quantitative literacy, right? We can do computations with accuracy. We take the necessary steps. We have critical thinking, inferences from relevant information. We model mathematical information symbolically. Right? All of our O of N notation here with quantitative literacy. And then information literacy. We can evaluate information critically, integrate information to accomplish the planned objective to synthesize information, right? How do we find the right data structure to solve the problem for us? All right, our general structure and behavior of stacks and queues, including priority queues, linked lists, binary search trees, hash tables, and heaps. We identify the most appropriate data structure for use in a given set of requirements. We describe performance issues related to each data structure, identified in Objective 1 for basic operations such as insert, delete, and find. Right, every one we've looked at performance for insert, delete, and find. Demonstrate how to implement at least 3 data structures using the Java collections framework. Right, these are built into Java, the Java API. You don't need to write our own. We can override toString and equals of our collections classes. How to implement the comparable interface. We demonstrate the ability to create structures within structures using the Java collections framework, like a tree map of linked list or an array list of array list. This 2-dimensional array list thing here is huge. That's probably the most common one. Identify 3 classic O n log n and 3 O of n squared sorting algorithms and describe their general properties. Yeah, I mean, I think most semesters are stressful when they're remote, Rishi. That's personally me. And illustrate the execution sequence of recursive methods. We talked about recursion as well, right? We kind of track those. All right, folks, we got through the material. Folks are amazing. If anything is not clear, please do let me know. I'm happy to help clarify anything that didn't make a whole lot of sense. I know we did essentially a speed run through it, and it's been a rough summer. I'm sorry it's not the summer it should have been. I appreciate you surviving it with me. Excuse me. So, any other questions on the final project? I know one of the groups wanted to meet tonight after class. We can chat with them and see how it's going with the final project. Again, the idea here is we're just calculating all the possibilities here. Yeah, definitely. They're all archived out in YouTube, Rishi. So this idea with the Monte Carlo simulation is because we don't want to do all the possibilities here. Right? We want to do about 10,000 or so. So like, don't do all 2 million. This is going to take you forever. Take like a small percentage of that, and then do the 990 possible hands for each opponent's hand. Right? So take a sampling of these possible 5 community card combinations. So randomly pick a bunch of them. Right? 100 of them times this here, you're going to be at about 100,000. That's still going to be a lot, but that should run about too terribly. I don't know, if it runs too slow, take less. Don't worry too much about it here. I just want to see that, yes, we can do this sort of operation. Once we know 47 of them, or once we know 3 of them, right, it's less possibilities to make those 5 community card combinations. So all of that here then, open, yes. Goodness, that one. That's the button I wanted. Right, so with Hold'em hand, right, if you give it these shared cards here, right, adding the shared cards here, it can find the best possible hand. So a Hold'em hand is 2 cards, given 5 shared cards. And you're welcome to modify this as well and tweak it. Not a big deal. Any way you folks want to go about that, it's okay. Just use that as like your starting point here. When I know what all 5 community cards are, and I know what my 2 cards are, with the 45 left, there's 990 possible 2-card hands. So this is probably the easiest way to go about that. Just always find 990 possible 2-card hands, right? Generate a bunch of possible 5 community card combinations, and then figure out what your chance of winning are. Right? Each of those 2-card hands is going to go and try and find the best possible 5-card poker hand, given all of its possibilities. And that's okay. That part's done for you. Right? But we need to find what are the 990 possible 2-card hands, given a sampling of 5 community cards, a bigger sampling of 5 community cards. We can do all the different 5 community card combinations and easily here. So as we get closer and closer and closer, our odds will be more and more and more correct, because we're actually going to figure out all the possible outcomes for this one. We'll find out all the possible outcomes for this one. This one you'll probably do a sampling of, because otherwise you're at 990,000. You're at almost 1 million. You don't want to do 1 million calculations. And this one we're just let's just take 10, right? 10 samples and see what we get. Again, 10's probably not enough, but we want it to run relatively quick. So we got different choices there. Right? About 10,000 or so should run relatively quick for you. If that's super slow, let me know. We can take a look and see. But the idea is, I know what 50 cards are, so just pick, say, maybe 10, 20 different 5-card combinations out of that. Yeah, so you'll need to go through the deck, essentially. So the deck here, when you make a new deck, it puts all the cards in, and you can deal a card. If you know what a bunch of cards are, deal a card, and if you've seen the card, don't keep it. Right? So if I have, let me start up a new, clear my canvas here. Right? If you have the Ace of Clubs and the 3 of Spades, right? Spades, clubs, and then there's 5 community cards. Maybe you have a King of Diamonds, maybe you have the 7 of Hearts, maybe you have a 4 of Hearts, maybe you have a 3 of clubs, and then maybe you have a, I don't know, an ace, why not? I don't know, Ace of Diamonds as well. Sure. Right? Take a brand new deck and deal out every card. If it's one of these, don't add it. Once you've dealt them all out, you'll have 45 left. Right? From that 45 cards, right, to get all the possible combinations here, you want the 0th and the 1st, the 0th and the 2nd, 0th and the 3rd, 0th and the 4th, on and on and on and on. And then take the 1st and the 2nd, the 3rd, the 4th, the 5th, on and on and on. This is going to get you the 990 possible cards. With those ones. To generate the community card possibilities here, we're going to do the same idea. Take your deck and deal out cards. Take the ones out that you've already seen. Whatever's left, then you have an array list of, in the case of 50, just take 5 different ones out. And then pick 5 different ones. Make those 5 community cards. Pick 5 different ones. Make those 5 community cards. Pick 5 different ones. So just use random numbers. Just make sure you're not getting the same card twice. That's going to cause all sorts of problems there. Right? So make sure you're not getting repeats. Make sure you're getting 5 different indexes out of that 50 or out of that 47, out of that 46. And with 46, you're just doing all of them anyway. Right? You can do all 46. When you have the 47 remaining cards, probably even 100 might even be too long. Maybe do a couple less. Appreciate I'm working on getting all that stuff in. It's been a terrible summer for getting stuff graded. I apologize. Definitely has not been my best summer. I'm working my way through. I'm hoping to get caught up. Probably this. I'm working on it through this weekend, but I don't think I'll be fully caught up by next week. So I'm hoping if we don't have lots of class meetings, I'll have lots of time to be grading the stuff as well. Does that make sense, Dusty, for how we can pick these 5 community card combinations? Okay, yeah, so just like whatever is left in the deck, just pick 5 of them. So pick a random number between 0 and the length of the deck. Right? Just make sure you don't have any duplicates. So you'll have to do a little bit of checking there, but just pick a random number from 0 to the length. And then another one 0 to the length, another one 0 to the length, another one 0 to the length, another one 0 to the length. Yep, and that will be one set then of 5 community cards. What do you mean check that the hand is unique? Like, just make sure when you pick 5 different indexes, they're 5 different numbers. So, like, don't get index 1, 7, 7, 2, and 9, right? Don't have duplicates. Like 1, 7. If you draw a 7, pick another one again. Like, how about then 15, 2, and 9 or something? And then you can say, hey, the remaining deck, give me these 5 cards. Start with 5 cards, replace 1 each time until you've been through the whole... So, you remember, we're not going to be able to do all the possibilities. Like, you're not going to do all 2 million possibilities here. So, just pick a couple different combinations. I mean, start with 10, see how fast it is for you. Or maybe even, like, go to 46, because you're already doing 46 here. Something. Whatever number it is, and it doesn't matter all that much. We're saying, with this idea of the Monte Carlo is, we're just going to do a sampling of the possibilities. And we'll say that is probably going to get us relatively close. And again, the more sampling you do, the closer you're going to get. But we're saying we're not going to do all 2 million. If we do 1% of that or something. Even a third is a lot, Dusty. I mean, depending on... So, like, if you start with when you have all the community cards already done, start with this one. Right? And then go, when you do have the turn, there's 46 cards remaining. You know what 4 of the cards are? There's only 46 other cards that could be the 5th card. So you can do all 46 combinations of 5, and then from there do what you've just did up here with those 46 combinations. And then from the flop, when you only have 3 cards, we'll just do some of these. You don't need to do all of them to get all the possible 5 community card combinations. Just do a sampling of those, of whatever's left. So I know what 3 cards are, right? There's a bunch of possibilities for other 2-card pairs. Let me just try 10 of them or something to start. Does that part make sense? So kind of build your way through it and work your way up to it. So get the odds from the river first, where you know everything. Then get your odds from here, where you only have to do 46 possibilities. And then work on this one, where you have to do a couple more possibilities. Okay, those are good questions. Okay. Yeah, great. Yeah, again, if you folks get stuck on anything, let me know. The goal is everyone has a successful project. Right? So, like, when you're at the river and you know what all the cards are, there's nothing that's random. Because you know what all 5 community cards are. So you know there's only 45 left. Of those 45, you can make 990 possible 2-card opponent hands. You can run the odds for all 990 of those by actually generating all 990 possible hands and seeing how many times do I win, how many times do I lose, how many times do I draw out of those 990. So you'll have your exact odds of win, lose, and draw. Yeah, oh yeah, pre-flop, yeah, just pick random. And that's the idea with the Monte Carlo simulation. Because it is actually going to be actually random, there's no like distribution happening here that we need to be careful about how we're picking. We just pick 10, 20, 30, 40, 50 different possible 5-card combinations, and that is our substitute for what is it actually going to be. Now, what you don't want to do is do some sort of loop that says, okay, always take the first card, always take the second card, always take the third card, and then let's just randomize 4th and 5th. That's not going to be random enough, because you're keeping those fixed. So you want 5 random numbers every time to pick 5 random indexes every time. Right? So pick 5, pick 5, pick 5, pick 5, pick 5. Just make sure there's no duplicates there. Right? So just pick 5 random indexes, grab those ones out. Pick 5 more random indexes, grab those ones out. Pick 5 more random indexes, grab those ones out. And say, that's my community cards. Well, I'm going to use that sampling there to represent all of the possibilities. And again, I know 10 is not very much at all. Like that's not even close to 1%, but 1% is putting us at like 2,000 still. Right? Take off 2 zeros. We're at 20,000. Oh my goodness, yeah. Like 0.1%, it's still going to be a lot of combinations here. I know this is all known, it's all figured out, there's tables with all this information in it, and we could eventually just let it solve itself, but we don't want to spend that much time on it. We just want to simplify it for us and just take a quick little sampling and see what we're going to get. Excuse me. Great, all right, you take care, Rishi. All right, folks, why don't we send a raid off to somebody else in Twitch land for fun, and we can go from there. Again, if you've got questions, thoughts, concerns, please let me know. The goal is you folks are successful and you have a good project that is something you can actually talk about and should be a lot of fun. A great thing to talk about in an interview. Dad joke, you got it. I just found a good one, actually, for you folks. Let's see. I saved it here. All right, we'll switch back to the other camera. We'll switch back, right? All right. So I just found out my son was really interested in yardsticks and measuring things, and I don't know, like there's something fun about the really big, long yardsticks, and like you can measure all sorts of fun things about it, like how tall is the table and this or that. But he was really concerned when I told him they weren't going to be making them any longer. And then he realized I tell dad jokes all the time, and he just groaned at me. All right, awesome. So let's go see who's around. Gonna watch Lantern Noir and the Dungeons and Dragons crew again, or Void's doing some cool crafting. Rob, oh, looks like he's here. If you want to do Kubernetes, that could always be fun. Some other fun people. Chess is playing. I don't know what they're doing. Who Arena Kings? Or music. You're just gonna go hang out at Kubernetes. All right, let's go raid Rob. RWX Rob, right? All right, we'll head over that way. All right, folks, you take care. I will see you around. Please let me know what I can do to help. And no plan for next week streams, so just let me know if you want to meet up. We'll go from there. Take care.